This is the Physics 1 Lab 1 on constant velocity by Lucia Vacker. In this presentation, I'll be talking you through the introduction, the setup of the experiment, how we analyzed the ball's motion, how we created computational data and the model, and then we'll be comparing the observed versus predicted data on a graph and looking finally at the errors, discussion, and conclusion of this experiment. So first of all, for the introduction, the purpose of this lab is to measure the constant velocity by calculating the change in position over a set interval of an object. Then, using the results we obtained, we can create a computational model and compare it by a graph with the actually observed data that we were collecting with the tracker app. We make a couple assumptions in this lab. We assume that the effects of the air resistance and friction between the table are negligible, and that the only movement is the x-axis, or that the can rolled completely straight. And then just a preview, our results. Initially, our data followed the model we achieved, but with time, the air resistance and friction made our data deviate from the model. We also apply some physics. Since there's constant velocity, we use Newton's first law. The net force action on a system is 0. We also apply Newton's second law. Net force acting on a system is equal to the product of the acceleration and the mass, as long as the mass remains unchanged. We then also use these two calculations that I have up on the screen. In order to represent the system, we made a diagram. So on the left side, we have the initial forces acting on the can shown from a side view. So we have the normal force pushing up and the gravitational pushing down. And then we also have the applied force, which is the pushing of my hands against the can, which initially creates the motion. And then after that initial push, we have the final diagram on the right, which shows just the normal force and gravitational force acting on the can, since it's moving at constant velocity now. So for the setup, I used a tape measure to calibrate the tracker's distance, and then used two markers to mark 0 and 1 meter, choosing right as the positive direction. And then we used a flat surface with minimal friction, and a dry shampoo can, and then a cell phone camera to take a video. Then we use this tracker app to calculate and to record the position of the can at each time period, which is shown here. And we chose the middle of the can to be the marker position for the tracker. Then we have these calculations that we made. As I mentioned before, we used these two calculations. So we looked at the initial position, final position, and found the change of position. And then we did the same thing for time. The measured mass of the can was 0.243 kilograms. And we calculated the average velocity to be 0.5946 meters per second. Using the tracker app, we were able to find the initial and final velocities. And then we were able to put that into our model of the code in order to create our predicted data. So here I have my data up. Over here you can see I added the 0.695, which was our initial velocity, to the code. And I was also added the mass up here, and we made some adjustments to the data here to reflect Newton's second law. Basically what I've just said, we added the measured mass, time interval, initial and final position, and the calculated initial and final velocities. And then using the predicted points that the code gave us back, we were able to plot it against our actual to create this graph. As you can see, the predicted data is slightly above the collected data. So we have some similarities here. Both data sets are linear, and the slopes are both positive in the upwards direction. And then we have some differences as well. So the predicted slope is greater, which creates a widening gap between the lines. And also the model doesn't take into account the frictional forces that the can inevitably experienced, which is shown more and more over time. So for our errors, there's more than one axis, and as I said, the movement of the can was not completely straight, it's slightly deviated. Also, we had some rounding of the calculations, which makes the results slightly inaccurate. Also, the tracker placements are not always directly in the can center, affecting the accuracy of the predicted graph. For the discussion and conclusion, graph starts with two velocities being very similar, but as the object moves, the actual data slows down since there are frictional forces. Therefore, with the passage of time, the difference in accuracy of the prediction worsens, and the gap between the line becomes bigger. The net force becomes non-zero as the friction acts on the can, and therefore the can experiences a negative acceleration. For some further questions, we look at what if we flip the axes? Nothing would change necessarily except that the direction of the slope would be negative, instead of in the positive direction. And that's just as if we had chosen that the left, going towards the left, was the positive direction instead of towards the right. Is it possible to say how many forces are added together to give zero net force? Is the zero net force justified? I don't think the zero net force is justified, since we saw that there was actually frictional forces being used. At the moment, it's hard to tell how many forces are added together because we weren't able to measure the friction acting on it. But if we were able to add that to our model, it would be more accurate data. Thank you for listening.